Welcome to the course Business Analytics and Data Mining Modeling using R. So in the previous lecture we started our discussion on another technique K nearest neighbors or KNN. So we discussed most of the theoretical part, the discussion, what KNN is about, the difference of KNN from KNN being the data mining technique, the difference of it from other techniques like statistical technique, multiple linear regression. So we discussed all those things. We also did an exercise in R where we used the Sedan-Carr.XLS data set and did the partitioning, normalization, and then the modeling. So we also looked at the results, and so the next important aspect of KNN is that the selection of this value of K. So appropriate value of K, the optimal value of K, how do we find out that? So in the previous lecture, we in our small exercise that we had done, we had used the value of K as 4 for the illustration purpose, but the optimal value of K could be different. So how do we find out that? So first we need to understand certain things about this particular aspect of KNN, the selection of choosing an appropriate value of K. So for example, if we take K value as 1, value of K as 1, then this is going to be a powerful technique, especially for a large number of records in training partition, because K being 1, fewer number of computation, distance based computation would have to be performed, and because the value of K is 1, so that means we are essentially dealing with just one neighbor, and therefore using this just one neighbor, the class of once we identify the closest neighbor, the class of that neighbor itself is going to be the predicted class of new observation. So for example, the plot that we had generated in the previous lecture, if we are able to use that plot, then this one. So for example, if this is the new observation represented by X symbol, and if we are able to find if we are required to find just the one closest neighbor of this new observation, then it would be probably this point. This point seems to be the closest point. So the class of this closest point would actually be assigned to this this particular new observation. So if the value of K is 1, then the computation, number of computation would just be 1. The distance between the number of computation would be much less, and easily we can classify new observations and assign the same. If the value of K is greater than 1, so as we move towards higher values of K, the smoothing effects will start to take place. Smoothing effect in the sense, because if the value of K is more than 1, let's say 4, 5, 6, 7, or even 10, then the different more number of neighbors would actually be used to classify the record, and therefore it would in a way control overfitting issues. When we have the value of low value of K, or let's say K is equal, if the value of K is 1, then we might end up fitting to the noise. So therefore if we have a larger value, then that smoothing effects will in a way control some of the overfitting issues arising due to noise. So the next point exactly talks about this, that low value of K, it might lead to more chances of fitting the noise. If we opt for a high value of K, then more likely to ignore the local patterns in the data. If we are going for high value of K, then we might ignore the local patterns, because the smoothing would be heightened, and therefore those global effects would actually be will be the dominant effects, will take dominance, and the local patterns might be ignored. So therefore we have to trade off between benefits from local pattern versus global effects. So if we if we target local pattern and we select a smaller value of k, we might end up fitting the noise. So therefore we don't want that. And if we go for the global effects and go for the smoothing effects, so that we are able to control overfitting issues, we might end up ignoring the local patterns, and we might end up ignoring the predictors information as well. So for example, if we take the next point being, if we take the value of k as n, that means all the observations that are there, then that would essentially lead to naive rule, that means majority rule decision. So if we take all the observations, that means the class which is the most prevalent among all those observations, that would be assigned to the new observation. So irrespective of the predictors information, so we would end up ignoring the predictors information, and more often than not, almost in all the cases for all new observation, the majority class would be assigned. So we don't want this situation as well. We would like to balance between ignoring the predictors information and also fitting to the noise. When we have low value of k, we want to fit to the local pattern, right, the genuine patterns that could be there, and we would not like to fit to the noise. When we have higher value of k, we would not like to ignore the predictors information or too much of smoothing effects. So we need to balance out the local patterns and the global effects, incorporation of predictors information, and avoiding the fitting to the noise. So let's move further. Now value of appropriate value of k will also depend on nature of data. For example, if the data that we have is slightly complex and carries the irregular structures, then we would probably be better off having low value of k, right? Because the global effects might not be suitable, higher value of k, and therefore global effects, the smoothing, might not be suitable for this type of data, and we would be better off capturing the local patterns because of the complexity that is involved in the data. However, if we have regular data set, regular structures which we are familiar with, in those cases it is higher value of k might be preferred, right, because we understand those structures, and therefore we would be better off focusing on the smoothing effects, so that we are able to control the overfitting issues, or which mainly arise due to fitting to the noise. Now we look at the typical value of k that could be generally that is suitable. So between 1 to 20, so typically this is so we take a value of k between 1 to 20. Now even within this range, the odd value of k is preferred to avoid ties in a majority class decision. So because we are in a classification task, discussing classification tasks, so there when we have to make our prediction decision using the majority class rule, once the k neighbors have been identified, then there if the value of k is even number 4, 6, 8 or 10, then sometimes there could be ties two classes having, suppose if the value of k is 8, and there are two classes, one having 4 neighbors representing that class, the other class is being represented by remaining 4 neighbors. So in that case there would be ties, and it would be difficult to assign the new observation, to assign the new observation. Therefore, to avoid those ties, the ideal value of k would be the odd value. Now having discussed all these points, the low value of k, the high value of k, the nature of the data, the structure, whether it is complex and irregular or regular, the typical value of k and the odd value. So having discussed all these points, how do we find out the best value of k? Shouldn't it be based on the performance? So the classification performance on validation partition, it could actually be used to find out the best value of k. So what we are going to do is we'll try to understand through an exercise in R how do we select the best value of k. So let's open RStudio, and the data set for this exercise that we are going to use is the same data set that we have used in the previous lecture. So that is the Sedan card data set. So we already know 3 variables that are there: the household income, the income, annual income, the household area, and the ownership. So what we are going to do is there are in this particular data set that we have total number of observations are 20, and out of these 20 observations we had partitioned 15 observations into the training partition and the remaining 5 into the test partition. We were also able to we also built a model in the previous lecture using for k value as 4, right. So so now what we are going to do is different possibility. The possible values of k could be from 1 to 15 depending. So these are the observations that are there. 15 observations are there in the training partition, and these are less than the typical value that we talked about 1 to 20. So therefore we'll run a loop for all these 15 times. So k value of k could range from 1 to 15. So in the so what we are going to do is for different value of k, we would be building a K-NN model, and for each of those models we would be predicting the class of observations that are there in the test partition, as well as we would also be re-scoring the training partition. We would be predicting the training partition observations of training partition itself, right. So and then we would be recording the errors, misclassification errors in the training partition and testing partition. So as you can see, we have initialized these 4 variables, 4 vectors: mod train. So that is for modeling, that is for the modeling using the training partition, and then scoring the training partition itself. Then the next one is mod test. So this is for scoring the test partition, and so let's initialize this. Then we have error training. So this is the misclassification. This variable is to record the misclassification error in different training partition for different values of k. Then we have another vector, another variable, error test, to record the misclassification error associated with different values of k for the observation in testing partition. So once this is done, we can run this loop. You can see that for both the training and test partition, as usual, we have selected the first 2 variables, numerical variables, the income and household area. You will also see that the one difference between these 2 lines of code is that this third argument, that CL function, this remains same. So the training of the finding the k neighbors would be based on the training partition, and it is the test partition that is different in these 2 lines of code. You can see here it is df train. So we are building the K-NN model on the training partition, and then the scoring the observation of training partition itself. And then in the second line of code, we are building the K-NN model using training observation, that essentially means identifying k neighbors, and then scoring the observation belonging to test partition. So and every iteration for every value of k, we would be recording different errors, and we would be running doing the scoring, building these models and doing the scoring for training and testing partition. So let's execute this particular code. you would see that different variables have been created. The right now we would like to focus on error test and error train. So you can see two numerical variables in the environment section having 15 values, right. So once this loop has been executed, we can move to the next line of code. So we are constructing a data frame where the first column is representing the value of k, that is between 1 to 15, and then the second column is error training. So that is has been captured in this particular variable error train, and the third column is for misclassification error, that is error validation, and has been captured in error test variable. So let's construct this data frame. Now we are interested in just the two values after decimal points. So let's round these values. So these are the values. So this is the output you have for value of k. When the value of k is 1, you can see the training error is 0 and the validation error is 0. So when value of k is 1, so essentially we are going to use just one observation. So if we look at the training, so for any observation in the training set, we are going to use just one close by observation, right. So this is yielding this result that error is 0. So almost all the observation using the value of k, they are being correctly classified. The same is applicable in error validation. So there also, as we can see that 0 value is there. Typically this is not the case. This is mainly because of the way partitioning has been done. So if we look at the different values of k, so you can see for value of k as 2, the error training is 20, then for 3, then 4, and then 5. The error keeps on increasing as we increase the value of k. So as we move from 1 to 15, the error in training partition keeps on increasing, and if we look at the error validation, it remains at 0. So this is peculiarity about this particular data set. This particular partition is actually being captured, not the typical case. You would see only at the k value of k 14 and 15 we see the different errors. So probably we need to run these partition, do this partitioning and do this modeling again, because some peculiarity about the this being a small data set, just 5 observation in the validation. So that is being captured and we are not getting a typical kind of result or closer to typical result. So what we will do, we will will execute the partitioning again, and then again we will execute the following code. So let's do this. So again the 15 random, we want to we would like to have different 15 observation in the training partition and 5 observations, so that we are able to get a typical result. So because we are using a small data set, so that is why some peculiarity in the results can be seen. So let's execute this. You can see we are recreating these partitions, and hopefully we get different partition this time, and therefore different results. So we will have to run from here once again. And we will execute this code, and let's construct this particular data frame again. Now there is some change there. You can see some change, you can notice there. So still, even if we look at these results, the error training, as you can see, for different value of k, this keeps on increasing. So it increases, then slight drop there, and then again it keeps on increasing with few drops, and we are mainly interested in the validation error. So you would see the again in validation itself, again we see some peculiarity in the results. So what we actually expect is that the error in validation would actually increase initially, and then it would decrease, and as we go along for more values of k, it will increase further, right. So there is going to be a minima, right. So we are interested in the very first minima that could be there. So because of the smaller data set, we are not able to see those kind of results. So what we'll do, we'll try once more. So as you can see, I am reinitializing these variables and re-executing the loop, and then again, and now I think, yes, now this time we are getting more typical results. Yes, this is a more of a typical scenario. So we have a good enough sample size. Probably this particular result is replicating the regular scenario. We have a larger sample size. So here you can see that error training, it starts from 0, right, and then in the validation it starts from a higher value, and then as we increase the value of k, it goes down, and it remains, again some peculiarity are still there, but still it is better than the previous cases. So it keeps on, it decreases or remains same, and then further it increases at the extreme points. So so optimal value of k would actually have to be identified using the error in validation. So the error in validation would typically be more than the error in the training partition, because we are building the we have built the model on the training partition, and in this case KNN. So essentially we are identifying the using the same observations to identify k neighbors, and using those k neighbors we are trying to classify the observation of the same partition, training partition. You would see in the training partition starts from 0, then error keeps on increasing, then again few dips, and then further it increases. So typically validation error will be start with the higher side, and then it will decrease and it will increase further. So if we look at the data, then probably value of k is equal to 3 is the optimal value, where we see a direct dip in the error value from 40 for k of value of 1, and k value of 2, again the error is 40, then there is a dip and it becomes 20. So further if we keep on increasing these values of k, the results, the error results don't change, error rate doesn't change, and later on as we reach to the value of k as up to 14 and 15, then again there is an increase. So let's use this particular result for our further discussion. So we can draw a plot between the error rate and the value of k. So we are mainly interested in the validation error. So let's look at the range 20 to 60, and we'll have to specify this range here. So appropriately covered 0 to 65, it would be covered there, and 0 to 16 the limit on x axis, so it would be covered. If we look at the range of error training, and that is between 0 and 46, so this will also lie within this range. So this particular range for x and x axis and y axis, they are appropriately specified. So let's generate this scatter plot. Now this is the scatter plot for validation error. So this typically would be more smooth if there are more more values of k to choose from. So in that cases, if we plot a smaller number of values for k, then again the plot would look like this. But if we have large number of values for k to pick from, then the larger sample size, then the error values will also smooth out. So this curve would be much more smooth. Let's also plot, let's also add the curve for training partition. Now this is the curve. Now we look at this, let's zoom in. If we look at the plot, you would see that in the training case, as we start from 0, the error is on the lower side, and as we keep on increasing the value of k, the error keeps on increasing, right, few dips here and there, and then it keeps on increasing. So we look at the validation. The validation error is always above the training partition error, right. So it starts from higher value, then it decreases, right. So this is this kind of curve that we are getting. This is mainly because of the smaller data set that we are using. If we want to know a typical curve that we would actually expect would be something like this. So probably if we are having a larger data set, so what is expected is that these are value of k, so different values of k on x-axis, and here you have error rate. So this could be on the validation partition or on the training partition. So typically the training error rate on training partition would be on the would be smaller in comparison to error rate on the validation partition. So validation partition, it will start from higher side, and as we increase the value of k, it will probably decrease, and it will reach to the minima, optimal minima, and then further it might increase, and in that fashion it might go. So this typically this might be applicable for validation. If we look at if we want to understand the curve for training partition, so again if we believe that for low value of k, our model, right, our K-NN model, if it starts fitting the noise, then even for low values of k as well, the error should be on the higher side. But essentially when we are talking about the training partition, especially in K-NN case, the error is going to be much lower, right. So it might start somewhere between this range, right, and the as we move further, so the error it will come down, right, and as we further for more values of k, again it will come up. So this would be mainly applicable for training. Now in this particular range, if in this particular range for values of k starting from k0 to starting from k1 to a few smaller values of k, if we are not fitting the noise, then probably this particular curve would actually drop further, right. So this might be like this. So different variation for this particular, depending on the data set, and depending on the modeling exercise that we have, depending on the predictors information that we have, and how much the model is able to, how much better the model is able to classify. So this is the typical scenario that we expect, which is in a sense, in a rough sense, is reflected here in this particular curve, but we had to do many iterations to reach to this particular result. Reason being, we are dealing with a small data set, and therefore for this small data set, sometimes the results might not be as expected in a regular scenario. So it is therefore recommended that a larger data set should actually be used in a data mining exercise, so that we are able to get the usual results and then analyze the same. Now once this is done, once you have a table of this kind where you have the error values, so you would be interested. So in this particular case, we are just dealing with 15 different values of k. So it is easier to spot the best value of k out of all these values. So it is probably the k is the value is 3. So it is easier to spot in this case. So probably the best value of k is 3. But if you are having a large number of we are trying out this particular exercise for a large number of values, so we can use this particular function minimum and find out the minimum of these values. So you can see this is 20. Now for this particular value we would like to find out the lowest value of k for which this particular error was achieved. So for different value of k, this particular error could be the lowest error. There could be many minima, there could be many minima points. So this particular graph could also be different depending on the different data set scenario. It will go come up and down and in this fashion. So there could be 2 such points. So how do we find out the best value of k? So it is generally the first one, it is generally the first one that we would like to pick. So this is the value, so this is the value of k that we would like to pick, because here it might be fitting to noise or some peculiarity in the data set. So it is generally the first one that we pick. So we can do this using this particular code. So in the brackets you can see for in the row side we are trying to identify the index where this particular value would be, this minimum value would be there, right, which dot min, and the very first. So for different values, indices of all the rows where this value of 20 is there, they would be there in the result, but we want to pick the first one. So that would be selected here. So you would see that 3 has been selected, which we also had identified by looking at the table itself. So we were dealing with a smaller data set, so this was easier for us to do that. Now once this exercise is done and we have identified the optimum value of k, now we can also see how we can actually use this optimum value of k and predict the class of a new observation. So the in the scatter plot that we had generated, we had used this particular new observation, annual income 6 and household area 20. So how we can score this particular observation, how we can classify this observation. So again you can see we are using KNN function, and training first argument is the training partition that we have specified. Then in the test we have specified just 1 point, it's not the test partition, it's just the new observation 6 and 20 using the combine function. And then the class is for the in the third argument, it's the classes ownership variable from the training partition. Then k value, as you can see we have picked up the best k value, and let's look at the classification. So this particular observation would be classified as owner as per our model. If for a different point, let's say 5 and 15, this observation having income as 5 and area as 15. So let's run for this as well. Let's score this one also. This one also would be specified as owner. So in this fashion, for specific points we can classify them using KNN, and we also had a look on how for a test partition we can score it. We looked at how we can identify the optimum value of k. So we'll stop here, and we'll start our discussion in the next lecture for the remaining points of KNN, and also how KNN could be used for the prediction task. Thank you.